what if in some certain cases, this reaction somehow A plus B to get C, right? But C itself also can decompose back to A and B. C itself can be decomposed back to get B and A and B. So basically what we can conclude is, even though A and B give you C, right? But C decompose back to get A and B. So this reaction, so-called, is actually in the equilibrium reaction. Okay, give me one of the reaction name that is in equilibrium. What is the reaction actually in equilibrium in your POC? What is the reaction you learn from POC? What are the reaction you learn? Cannot remember already. What about esterification? What is that? I need to look at your POC and then take back. Have to retake again. For example, that reaction, right? The reaction take place in forward and backward. Okay, let's look at the one of the real examples. Okay, nitrogen plus 3 hydrogen give you the 2 NH3. So for this reaction, right? This reaction, basically this reaction, it can be divided to 2 phases. One is the to get NH3. Okay, the product that you get here. First, the product is NH3. Secondly, the NH3 also will be decomposed back to N2 plus H2. Okay. So for this, the first one we call forward reaction. Okay, because the reaction moves forward. Forward reaction. On another hand, NH3 also can reverse back to N2 plus H2. Okay, we look at the rate constant of each reaction. Because you see, this is 2 different reactions, 2 separated reactions, but somehow it's taking place in the same reaction. So the forward reaction, the rate constant is K1. K1 so small, I write bigger. I want big. The reverse reaction is actually K2. Kindergarten 1 and 2. Okay. And this reaction, let's say, okay, because the reversible reaction is more complex. Hey, don't say F word in my class, Otherwise, I will F back, Okay. This reaction is actually the elementary reaction. So what is this elementary reaction? Recap. So it means that the order of reaction is the same as order of reaction, same as stoichiometry. Okay, let's consider, let's say we take one of the species. So now we want to find out what is the relationship between K1 and K2? Okay, because K1 and K2 definitely there is the relationship. K1 to get ammonia, K2 the ammonia decompose. So in order to find the relationship, we have to look at the one particular species, which is N2. For the first forward reaction, N2 is the reactant. Alright, it's the starting material or reactant. But N2 here is playing different role, right? For the reverse reaction, the N2 play as products. Okay, let's say if this reaction is taking place, N2 reactant become NH3. Later NH3 decompose back to N2 plus H2. The reaction take place forward and backward at the same time. Okay? Until it reached to the point that this reaction is in equilibrium. So how this reaction is in equilibrium? Because NH3 it actually formation at the NH3 forming at the same time as the same rate as NH3 decomposing. Okay, in that one point of time, NH3 formation will be the same rate as NH3 decomposition. Okay, in that point of time, one point of time. This point of time is represent reaction in equilibrium. EQ, reaction equilibrium. So it means that the forward reaction is the same as reverse reaction. Can see or not? Someone want to show off, can buy McDonald's, Yeah, bojo, So basically the rate of disappearance of nitrogen, if we want to come out with the rate of disappearance of nitrogen in equation, the rate of disappearance of nitrogen is rate of disappearance of nitrogen. I'm talking about the forward reaction. I circle. This forward reaction, the rate of disappearance of nitrogen is minus Rn2 equal to K1 N2 concentration of N2 times the concentration of H2 to the power of 3. Okay, this is provided is the elementary reaction. We only consider the reaction reversible elementary reaction because this is the most simple one. Okay, whereas the K1 is the rate constant of the forward reaction. Remember, K1 is the reactant of rate constant of the forward reaction. What about the rate formation of N2 through the reverse reaction? Okay, for the reverse reaction, you see, because the ammonia, okay, the ammonia decompose back to the starting material, okay, therefore, the rate of decomposing of this ammonia, or it actually considered as the rate formation of nitrogen, right? Because we are forming back nitrogen. Okay, so will be Rn2 equal to K2 times with the concentration of ammonia squared. Don't disturb the class. I can be very nasty also, if you're still disturbing the class. Okay, eventually what happened here is, you see just now when I mentioned, eventually what happened is, the reaction of NH3 formation, it will be the same as the decomposition of NH3. That is the point that the reaction is in equilibrium. Okay, now we want to find, just now I mentioned, right, we want to find the relationship between K1 and K2. So we have to find out in the point that that particular one is actually in the equilibrium. In the equilibrium, the rate of disappearance of N2 will be the same as the rate formation of N2. Anyone follow me? Rate of disappearance, so it means that nitrogen has been consumed in the same rate as nitrogen has been formed. That is so-called in equilibrium. Rate of disappearance and the formation. Okay, therefore minus N2 equal to Rn2. So now when we subtract back, when we substitute back the minus Rn2, here minus Rn2, together with it actually equivalent to Rn2. Right? Okay. These two, you can see that these two are equal, provided this reaction is in equilibrium only. Okay, you can compare between the forward reaction and backward reaction in the case that that reaction is in equilibrium, because it's not all the reaction can be in equilibrium. Okay, so we use EQ to denote the equilibrium concentration. Okay, so we rearrange the formula. So what we have, okay, I swap back K, K, I put back on the left. After that, I put the whole thing back on the right here. So we rearrange the K, K1 over K2 will be the concentration of NH3. Concentration of NH3 square over concentration of N2 and concentration of H2. Okay, let's say if you look at this equation, I try to put this, but it's too far. Okay, I write it here. Okay, if you look at this carefully, when we rearrange the equation, right, what we have here is K1 over K2. You look at the one on the top here. The one on the top is actually the product. Okay, so basically this is the concentration of products. And to the power of, let's say I can maybe n over the concentration of reactants. Okay, why do I have to conclude this? Because in the future when you need to write the rate, the equilibrium constant, you know that, oh, I write the concentration of product first, divide by the concentration of the reactant. Okay, basically this is the rate constant of, okay, of K1 over K2. This K1 over K2 we can change to the equilibrium constant or big K. Therefore, when we have this big K, right? So now, you see the relationship between K1 and K2, we can get new equilibrium constant. Okay, the reason why we have to find out what is the equilibrium constant, okay, because sometimes in particular reaction, we want to find out what is the rate of reaction, what is the rate of the forward reaction and the backward reaction. You have to calculate, okay? And then, because sometimes you can see that maybe the rate formation is faster than the rate of decomposition, you can adjust the parameter accordingly to that, okay? So let's move to one of the examples. Okay, this one actually it's not in your lecture notes. I got extra for you. Okay. Refer to these examples. Okay. I need you to practice how to write the equilibrium constant first. Okay, before I ask you to do example 2.5. Okay. Write down the equilibrium constant for this following reversible elementary reaction. Equilibrium rate constant is the big K, right? So this big K, it actually equal to the concentration of products, the power of maybe N. Okay, I give you the general formula first and over the concentration of reactant. Okay, now can do, right? So I give you 1 minute. Try to come up with the equilibrium rate constant of this equation. Okay, 1 minute. I started timing already. Okay, I think you done already, This big K is equal to concentration of C12H10 times concentration of H2 over concentration of C6H6. Is that correct? What other thing is still missing, EQ, yes. Someone say, oh. Because it must be at the equilibrium. Anything else? Yes. Correct. It's the square, right? At the this C6H6. Anything else? Because this one you don't need, you can put or don't put also can. One. Okay, because this is the elementary reaction. So the coefficient here will be the same as the stoichiometry number here. I think you have to close the back door for me. I think the back door open, right? Have me to close it? Have me to close the back door. Okay, so now we move to something more excited. Okay, why I said it's more excited, I cannot say this one will be coming out from your quiz or not, That's why I asked your classmate to close the door, Okay, example 2.5. Well, this one they put two star. Because it's not 3 star. 2 star is very, very important. Die must know how to do. Okay, we look at this question together. This reaction is the dissociation. Okay, with dissociation, dissociation basically is the decomposition. Dissociation, right? PCl5. Okay, this PCl5 is decomposed to get 2 products. Why I say it is decomposed? Because one starting material, now you get 2 products. Okay, therefore this is so-called considered as a decomposing reaction. If we get PCl3 plus Cl2, and basically this is the, how do I know this is reversible reaction? because of this half arrow head, right? Okay, this is to indicate that this reaction is reversible. And the question asks to calculate the rate constant of forward reaction K1. Determine the value and the unit of the equilibrium constant K. Well, now it's like throw you into the water and then let you swim, right? Okay, first, before we do this question, right, we have to link back. We have to look back in order to find out the rate constant of reaction. What we have to write out first. Of course, this one is the one I asked you to practice. Okay? So in order to answer this question, you have to find out first what is the my big K is what? Big K is the concentration of what? PCl3 equilibrium times Cl2 equilibrium over PCl5 equilibrium. Wow, this one easy, right? Because this is the key of this question. Okay, but the thing is, later on you don't need to worry, we will go through together. So after that, we look at the information provided. Okay? The information provided, initial concentration of PCl5 is 150 km. At equilibrium, 65 km per cubic volume is dissociated. And this is the rate constant of the reverse reaction. Okay, the reverse reaction, because K is equivalent to K1 over K2. Okay, and now when you see this question, because whatever the concentration you put here, it must be at the equilibrium, right? It must be at the equilibrium. So when you see the word equilibrium, while your eye must be open already, cannot sleep. This equilibrium is to indicate that, okay, at equilibrium 65 kmol over m here is dissociated. It means that at equilibrium, the starting material, it will be dissociated. Is in what? It will be decomposed 65 kmol, right? So what I normally do is I will write a table, okay? Small table, not a big table. In order to do this question, okay, give me a second, I had to rearrange something. Okay, we have to find out the idea of this is very important. This one, I put 2 star already. Maximum is 2 star. So I don't know is how serious is this. Okay? No more 3 star. We have to find out what is the concentration of each chemical at equilibrium. Okay, how are we going to find out? First, in this reaction, right, there are 3 compounds, right? PCl5, PCl3, and Cl2. PCl5, PCl3, and Cl2. Okay. The question said that initial concentration, it means that at the beginning, the concentration of PCl5 is 150. Okay, the unit is I put upside here. Okay, because if I put the unit and it will be messed up with the number. So the initial concentration of PCl5 is 150. At equilibrium, it minus 65. Okay, because this 65 is changed by minus 65. You know where did I get the number 65? Because, yes, okay, 65 is dissociated. It means that, just to simplify the language, is the PCl5 is reacted 65 kmol. Okay? So basically, originally the PCl5 have 150 minus 65. So called, it means that when this minus 65, right, the product that you have, it also will be same number, right? Because PCl5, when it decomposes, it will give you 2 products, right? And that 2 products, it will have the same concentration as the amount of PCl5 is decomposed. 65 and 65. Okay, now the most important part is the at equilibrium. Because at this equilibrium, once we already finalize the number, we can put in this equilibrium, okay, and then we can get the answer. Okay, now we already finalized, right? The number of PCl5 at equilibrium is 85. PCl3 is 65, and as well as the Cl2. So when we put back order, we substitute the concentration. The value that we get here is actually the big K, right? Let's say I already substitute the concentration here. The value that we get here basically is the rate at equilibrium. Cannot see. Oh. Can zoom what? Zoom in, zoom out. Is that better? Okay. Blur. You mean my handwriting blur or you blur? Okay. This is the K. Oh, another important thing. This K remember when you get the number is as important as the unit. The unit of k must be correct also. Huh? Maybe this one 100 mark. You get the number correct, you get 49.7 mark. The get unit correct, you get 100 mark. Got what I mean? Is the unit of this calculation is as important as the number. So make sure that you know how to work out to get your unit also. Okay, your CRE is going to end soon, huh? Yeah. And then can go for what is your next class? CRE, PCI. Okay, I thought it's another CRE because I'm the only person who teach now. Okay. If we already have K, can we calculate what is K1? Yes. So K1 is? Because of this equation, right, K equilibrium equal to K1 over K2, and we know that K2 is actually provided. So after you work it out, K1 equal to 27.8 per hour. Any question on this, you just let me know. Huh? If you have no question, this will be our end of the lecture. Huh? And see you again tomorrow, right? How come? How tomorrow? I want to teach. See you next week. Huh?
Oh, wait, hold on.